Hello, and thank you for joining us for today's webinar, Additive Manufacturing 101. My name is Kim Kaloran with Stratasys, and I will be your host for today's event. For those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from 3D CAD files. Using our patented FDM technology, we manufacture and sell Dimension 3D printers, Fortis 3D production systems, and we also operate Red Eye on Demand, which is an online rapid prototyping and digital manufacturing service. In this webinar, you'll learn how additive manufacturing systems, such as 3D printers and production systems, are changing the future of product development and manufacturing. Now, without further ado, I'd like to welcome our speaker today, John Cobb.
Okay, thanks a lot, Kim. So I'm real pleased to be here today talking to you about additive manufacturing and Stratasys. As Kim mentioned, my name is John Cobb. I've been with the company for 15 years. I've had various sales and marketing and operation roles within the company. During the period of time that I've been with the company, we've grown from about a $4 million organization to today a $120 million organization. I'm pleased to be talking to all of you and look forward to a good discussion. And hopefully, if time permits, and I think it will, we'll be able to take some questions if there are any at the end. If we look at the objectives for today, we really have three things we want to focus on. One, what is additive manufacturing? I'll do a quick review of the different technologies that are out there at this point in time. I think it's always important to look at how people are using the technology, so we'll focus on a couple of application stories as well. And then, as I mentioned, we'll also take some questions. The additive manufacturing technology has really been known by a lot of names. You could say it kind of suffers from an identity crisis. Over the past 20 years, the names you see up here have been utilized, and so there's a little bit of confusion in the marketplace. But today, the idea of this additive fabrication has turned into the name of additive manufacturing. It's a term that's going to cover all the different technologies, and so oftentimes, or many of you may have heard the term RP, or additive fabrication. Additive manufacturing is the term today. In short, additive manufacturing takes in CAD data and builds parts in layers. Not to belabor the point, but to get into a little bit more detail, as defined by ASTM, you can see it's usually building layer upon layer as opposed to subtractive methodologies, so it's very green. And it's really a technology that early on was adopted in the design process, but today it really takes place throughout the entire manufacturing process, including end-use parts. And again, I'll talk about a few of those applications. The process is identified here, and what you do is you start with a solid model that is on the CAD file itself. It is pre-processed. In our particular case, we have something called a catalyst or Insight that does that, and think of that as a print driver. Once the part is processed, which would include slicing it and putting any necessary supports, that information then is sent to the system itself, which you see as number 2 there, produce the part, and once the part's produced out of the machine, you simply open up the door that you see there, and the part is delivered. There is some post-processing that is being done, whether it's our system or anybody else's technology, and what that does is simply clean off some port mechanisms that would be adhered to that product that you see there in number 3. Again, a simple additive process. And again, the very difference is that you're adding things, there's no subtraction. Oftentimes when I'm at trade shows, people think we're really utilizing a CNC process. I want to make it clear that it's not that. The name describes it. It's additive manufacturing. As I mentioned before, we're not the only one in the industry. I know a lot about the FDM technology. I'll go through here just a brief description of some of the other leading technologies. I'll start with the one that I know the best, which is the FDM technology. It's the technology that we use. It's called fused deposition modeling. We started the technology about 21 years ago. There's also a company called Bits from Bytes that utilizes the same technology. Real simply, what we do is we start with a filament. The filament is fed into an extrusion head, and we extrude out layers upon layers of thermoplastic, building up the part. And all the technologies do build layer upon layer. The second one is selective laser sintering. That is something you'll find in 3D Systems, or a company that's out of Germany, which is called EOS. They do have a presence in the U.S. and in Canada as well. That process typically takes a powder keg, if you will, or a powder supply, and utilizes a laser to actually solidify the powder itself. Once the part's completed, you move the completed part out of the powder bed, if you will, and then go through a variety of cleaning processes to do that. These machines are typically a bit more expensive than you'll find from the FDM technology. The next technology is called SLA, or stereolithography. This technology, SLA, is really the genesis of the additive manufacturing technology. So oftentimes, like sometimes facial tissue, you hear the word Kleenex, people will talk about the entire industry as SLA. In fact, it really is just a technology that's utilized by 3D Systems and most of the Chinese and Japanese manufacturers that are out there. The process here starts with a resin-based container. Again, it's using a laser. The laser actually then comes in contact with the resin and solidifies the actual part layer upon layer in that resin base. And slowly but surely, the finished part, if you will, emerges from that resin base. When it's completed, again, you remove this block, and then there's post-processing that has to be used to generate the final part. The next one is a little bit newer item, which is called jetting, which is simply an inkjet technology. And you're probably all familiar with inkjet printers from Canon or HP or whatever. And this really is no different than that. The only difference is that in the case of Z-Corp, the inkjet is used to jet a resin into a powder base, and the contact of that resin extruded from the inkjet as it hits the actual resin itself builds a solid part. So again, you pull the part out of this out of this powder base, and simply do some cleaning to actually get the final part. The object uses inkjet, but it actually deposits the resin right on the base surface to build up the part. The final technology is DLP, digital light projection, which is something, of course, you find in television sets today. There's two technologies that this is utilized, a company called Solido, and then also a company called EnvisionTech. And what both these companies do, deposit a thin layer of resin and then cure that resin utilizing the digital light process. And as the part is built up, the actual base then slowly sinks into this resin base, allowing a thin layer of resin to be cured layer upon layer. Once the part's completed, then there is a cleaning process that goes along with this. All these companies have a lot of information, I'm sure, on their websites if you wanted to go and get some more details. But that's hopefully a quick explanation of some of the technology. I'd say the bulk of the technologies that are out there today. We go back and look at the FDM specifically. What we have really can be classified as really four types of materials. And now this would be, again, speaking specifically of the Stratasys product, the FDM process. The most popular material that we have would be the ABS, and you see a couple derivations there. One, a solid ABS, and then another one which is called the M30i, which is a medical grade, allowing it to be autoclaved. You see a couple different varieties of polycarbonate. and also polycarbonate ABS blend. Fairly new products for us would be the Ultem and the polyphenol sulfone, or PPSF. Those are all products that can be extruded utilizing the FDM process. The next slide really starts to look at this classification of additive manufacturing. And today, there are really three types of processes or products that you can acquire in additive manufacturing. The first one is called a service bureau. And if you look at the service bureau, what you really want to do is think of the idea of Kinkos. And these service bureaus, there's thousands of them that reside throughout the world. And the idea being you send the STL file to the service bureau, and what you end up with is a part. Typically, you'll see a 3-day turnaround, and there's many technologies that I mentioned before that the service bureaus will employ in their companies. The next group is some group that was really introduced in 2002. It's called 3D printing. It's the most affordable solution, typically in the range of around $10,000 to $50,000 is the price point. You kind of think of the idea of more of a desktop type of an inkjet or laser printer as you start to think about this. You can see the price points. What they're really used for is they're simple, and they're really oftentimes used in the early design process to test for form, fit, and some functionality, especially with our products because they are able to produce out of ABS parts. The last group is called 3D production systems. These are high-performance systems, kind of using the same analogy here. Think of a high-performance like a Xerox Docutech or something like that as far as a technology. These products are typically then in the $50,000 to $500,000. Some, in fact, can be over $1 million. They're very much optimized for performance, so looking at things like feature detail, speed, a wide variety of material choices. And they really then, because you're paying this type of price, really then can perform any of the different operations that you'd find in a 3D printing. Most of the service bureau companies would employ one or several of these 3D production systems to produce parts. If you look at the uses, what's really interesting about the additive manufacturing process is that it can be used across the design process. It really started out in the 80s, late 80s, really as a way to communicate concept models, getting a little bit into the functional models. But as products have improved in their process, materials, being more reliable, being more accurate, you've also seen the additive manufacturing process move into manufacturing tools, jigs and fixtures, and then, of course, in some cases, end-use parts. If you look at it today, this kind of shows a curve over time. Where we are today on the curve, roughly about 80% of the business today is in 3D printing and about 20% in the production systems. So kind of, if you look at the lines that are progressing across there, we're kind of really at that first set of lines. But as time moves on, because there are so many much more parts produced than prototypes, over time there'll be we believe a proliferation of the 3D production systems, and again that has taken place really since the late 80s. Getting back to a typical design cycle, what you see here could be described by a lot of different companies, use a lot of different terms, but the idea is you start from concept and you move to production. And the way companies oftentimes employ rapid prototyping or additive manufacturing is really in that tooling process, right before you see the tooling area. So it's late in the process, and oftentimes when something's late in the process, you get something looking like this. Obviously, if you make changes earlier in the design process, those changes are less expensive. As people have started to employ rapid prototyping, especially early on, they tend to use it right where you see that red arrow. So oftentimes, some of the early design concepts and communication that could result if the models were looked at and utilized earlier cannot be realized. I'll show you some examples a little bit later on where companies are using the technology much, much earlier in the process and getting some very, very good results. But kind of continuing on, I guess, the stream of how it's being used today, this is a quote that I think everybody can relate to, is from a research firm. If a product is late to market by 6 months, 66% of its gross profit margin is lost. And if you kind of look at recently this whole idea of the cost of not having good quality, the cost of looking at design changes, if you look at the headlines today, you really see a company that's really moved from probably epitomized good quality for years and years, company Toyota obviously, and recently, now it's been several years now, but some of the problems they've had with some of their design, manufacturing, and then really what it's done to the entire company itself. I was recently reading an article in the USA Today that indicated the Toyota Camry, which used to be the most popular car, at least here in the United States, now sits on a lot 270 days. It's the worst performing car as far as sitting on a reseller or a dealer lot of any car in the U.S. anyway. And that changes from, it used to sit on a lot 7 days. So it really kind of drives home the idea of utilizing quality procedures early on. So all that really gets into what I'm calling here the ideal design process. And that ideal design process really goes into utilizing rapid manufacturing early in the concept stage for communication, then in the engineering stage as you start to make those design changes, and all the way through the detailed design. And as I'll talk about it with some of the application stories, we also see it in the tooling or production area as well. Let's then move into a couple of the application stories that I want to get into. And we'll start this from the concept models. I have a couple of stories that we have from some of our good customers moving through functional prototypes, and we'll end with end-use parts. If you look at the concept models and functional prototypes, which still is probably the most common, or absolutely is the most common application at this point in time, you see the real benefit as far as reducing time to market and lower cost. And you really do that. It's called here on this slide indirect benefits, but you think about it, it really is a tremendous communication type of tool that you can use. I believe Terry Wohlers, one of the industry experts, often refers to this. He says if a picture is worth 1,000 words, then is a 3D model or a prototype worth 1,000,000 words? It's certainly a possibility, but the real benefit is, in fact, communication across the entire company line from engineers, manufacturers to management, and then can move out even into the customer base as you start to really prove a design or sell a design. The first application story I have here is a company hopefully some of you are familiar with, Ducati. And the story here is they cut their development time by 20 months. And what they did, it's kind of interesting, they used the idea of bringing in a additive manufacturing product. And what they did was rather than just saying, okay, we're going to move and move to totally cut our production costs, what they looked at is saying maybe we have an opportunity to pursue a couple of alternatives. So as they moved through the production or design process, they really started looking at 2 alternative prototypes. And they were able to do this because getting the information back very quickly allowed a couple teams that they set up to look at some alternative prototypes. They did that through the process and then picked one of the designs that they wanted. And what you actually have then is you can see they saved a huge amount of money, $285,000 in changes, and very significantly, they did the actual work in 8 months, which was a 71% reduction. The interesting thing about the story is, you think about doing that, they actually did this, and they started off with 2 prototype builds, so 2 paths. And you take the 2 paths, they took the best ideas from these, and still were able to get these type of benefits. Pretty impressive story. The next one is one that I'm actually very familiar with and visited their site numerous times, Toro products. This particular application is in the Southern California area, and it's where they do sprinkler systems for commercial type of businesses. And they bought a machine early on with the idea of using it for design. What they've done with it then is they realized that, excuse me, because they're making it out of polycarbonate, they were also able to move to a test function. And they actually have a room where they set up, and of course, when you're doing a sprinkler system, you want to make sure you cover the entire area of water. And they set up a room. They actually take the prototypes and test them. So they don't even have to go to tooling. They can move these things, as the slide says, up to 100 PSI. They shoot them out, check the water flow, make some design changes. And you can see the dramatic savings they had over 2 years. Time, 283 weeks, $500,000 as far as the savings. But the communication on this has been tremendous, because I've been out there a couple times. In addition to the engineering group, they'll bring customers in, and they'll actually then get feedback from customers, because there's oftentimes a little bit of customization that has to be done as you start to look at these sprinkler systems in different applications. It's a great story, taking it all the way from concept into functional design, and then also into marketing. Let's move on to the spectrum, if you will. And next, we'll take a look at a couple of things from a manufacturing type of application. Here, a little bit different measure, but again, from a financial standpoint, you're looking at a lower cost, profits. Again, the whole driver here is time to market. What you're really getting, though, is I would call it freedom of design and the capability of doing, it says rapid response or maybe custom type of design, which is becoming more and more important as we move through, and people are looking for products that fit their specific needs. If you look at it for an end-use type of application, and we do have a number, I'll talk about one, it typically is more of a short-run production or maybe a bridge to tooling. And you think about it, what we're really doing here is eliminating expensive tooling, so it allows you to move right from the design to the end-use type of part. Oftentimes, you can get great finishing, but in this case, it may not be the same thing as an injection molded type of part. But what you're looking at, of course, because it's again an ABS, a polycarbonate, or an Ultem material, you're getting physical properties that oftentimes are 80% of what an injection molded part would be. Some of the examples as far as tools, jigs and fixtures, gauges, drill guides, alignment tools, tooling masters. There's a lot of different applications for a manufacturing tool, and this area right here, this manufacturing tools, is really one of the large growth areas specifically for us. I think it's for the whole industry, but going back to one of the things that we have, which is that thermoplastic, it really lends itself quite well to some of these ideas right here, whether it's ABS or a polycarbonate material or the polyphenol sulfone. A great example is another company that hopefully everybody's familiar with, BMW. This is a great story that really kind of gets into ergonomics, worker feedback, and then also the final output of the automobile. The story here is that prior to getting an FDM machine, BMW was using an aluminum fixture to actually align the taillights and the headlights that you see in the top two pictures there. And this alignment tool was utilized by the workers, and we have a example of that, probably weighing around 8 or 9 pounds. The FDM part that you see there weighs maybe 2 pounds. And so there was a worker fatigue that was getting involved in this. The other thing that they solved was scratching the car. If you think about it, it's an aluminum piece. They were putting aluminum on this final, very expensive automobile that they have, and they had to come back in, not touch up every single one of them, but touch up many of them. And so what they were able to do is work with the assembly line workers. They had a number of different tests that they had, so they were actually able to interface with the worker to find the best possible design that was less fatiguing, easier for them to use. That's the design you see up in each one of these examples. And then because it's made out of the, in this particular case, polycarbonate, they were not scratching the automobile, so they minimized the touch-up type of work. But the interesting thing about this, they had a design, they tested the design with the actual people that are going to use it, and then got the design. So there's really total buy-in from all the users in this particular application story. So true customization. And here's a quick summary from, in addition to what I just talked about as far as the ergonomic benefits, you can also see that there was time and cost savings benefits as well. Another one that's, again, using an assembly tool is from a company called Oreck. You may not be familiar with those people as much, but they are vacuum cleaner individuals that have several operations here in the U.S. And they actually use the Fortis material for fixtures, and it's an assembly line process. And I think I have a slide here that will actually then show you how they utilize the parts from the FDM. Looking at the process, you can see it's assembly line process, moves from one to the other. And the whole idea here is it allows much faster handling, and as the process moves through, you can see they start to put the total components of that vacuum cleaner head, and this is facilitating much faster tick time as far as getting the actual part out. In this operation, last time I checked anyway, there were somewhere in the range of 20 different fixtures that Oreck was utilizing from ABS in order to assemble their parts. Pretty impressive story, because they do in fact make a wide variety of very small nuances as far as changes to their product, depending upon if they're selling it through, depending on what retailer they're selling it through. Each one wants a slightly different look to their product. So this allowed for a quick tooling changeover. So again, great use of customization. So looking at end user parts, again, kind of a quick summary here. Direct benefits, lower cost, shorter lead time. Goes back to the idea of getting to market quicker. From an indirect benefit, you see, again, end-use parts, mass customization, supports lean initiatives, much more design freedom and change of freedom, so adapting to your customer, in the case of maybe an end-user customer, or like in the case of Oreck and BMW, to a manufacturing customer. And, of course, reduction in warehouse space and inventory potential. The final one is actually an end-use part. An interesting story here. A company called Script Pro, which is utilized to fill bottled prescription. And as you realize, every single pill that you take these days have different shapes and sizes. And so what they were able to do is, as you see in the right-hand side of this slide, customize a chute, if you will, and which allows for the proper flow of different type of pills, which change very, very often. And the machine they wanted to have obviously the same. So this quick customization allowed them to do this within a matter of days, where it was taking them weeks before. It's a short run oftentimes for each one of these particular parts, But you can see the cost that would have been for the injection molding, which is about $32,000, a DDM cost of a little over $6,500, and again, you're building this particular item without any waste. So you build it up in a matter of hours. You're actually be able to customize the machine they have with this very simple bezel size. So a great story as far as an end-use part, utilizing, again, the value of additive manufacturing, which is that customization. So a quick summary. The terminology, we talked about that, additive manufacturing, looking at the various segments that are out there, the service bureau business, 3D printing. We talked about production systems as well. And then we moved into really the flow of the additive manufacturing, which can be utilized all the way through the development process from concept models, functional prototypes, some great examples of manufacturing tools, and then an area that's starting to get some traction, which is that whole idea of end-use parts. Enjoyed the presentation. I'll turn it back to Kim.
Thank you, John. In just 1 minute, we'll take a few questions that you may have. If you think of a question in the meantime, please be sure to submit it through the chat panel. I wanted to let you know that after the event today, you can find this recording along with the ability to request a sample part and also download other relevant materials at www.stratasys.com/additive_manufacturing_101. So please take a look at that URL for more information. Okay, it looks like during the presentation a couple of questions have come in that we have a little bit of time to take live now. Okay, John, there's a question here from Tyler who asks, what file format is accepted into the machines?
Okay. Good question. The most common file format you'll see is a .stl file. And if you look at it today, pretty much any of the 3D solid CADs packages that are out there, I'm thinking SolidWorks, Autodesk, kind of name the most popular, they actually output an STL file. So it's quite simple to move from your concept to a additive manufactured part.
Okay, great. Sorting through the questions here, here's another one that came in. This one is from Sharon. What is the size of the Stratasys machines?
Okay. As you look at our product line, as I mentioned before, we really separate the products into two distinct categories. So if you look at the 3D printing family, of which we have 5 products in that particular family, you start off basically with a 6-inch cube and move to roughly a 10-inch cube. And there's a couple of variations in there, but that's the size of the 3D printing. And then if you move into more of the production type of machines, you start at roughly a 14-inch cube and then move into a 36-inch cube. And of those products, we have 3 products that are in the production area. So if you look at the total Stratasys product line, what you're talking about are 8 different products total.
Okay. All right, looks like we have time maybe for one more question. Bruce is asking, what is the cost of a typical part?
Well, that can be a difficult question to answer because I haven't seen the typical part yet. But maybe what we can do is look at a part that maybe is kind of common to everybody. And so since I've been sitting here utilizing a mouse to go through this entire presentation, let's look at a typical, like a Logitech type of mouse, which would be primarily, again, out of probably a PC ABS type of blend or maybe just ABS. And it's obviously has electronics in it with a top, sides, and end. But if you look at that as a hollow type of part, what you're looking at from an ABS standpoint, which again is our most common material that we have, is somewhere, again, a little bit depending upon the size of the mouse, but somewhere in the range of $8 to $14 as far as cost per part if you own a machine.
Great. Thank you, everybody, for your questions. If we didn't get to yours live on the call today, we will be following up with you via email afterwards. We would like to thank each one of you for your attention during the presentation, and now I'm going to turn it back to our operator who will close out our session.